problem is that in Elasticsearch, it has a problematic scan query, which will try to manipulate the whole query cache. So this scan query will just read every context in the document. And as a result, it just stores a very long context. And in the schematic for query cache, it first just matches the query, and then we get the value. Even this long context, so most of the documents in the table, the Elasticsearch will not use this data for other queries. So as a result, all the following read or write query will hurt cache miss. And since this long scan query will run for several minutes, so it will manipulate the whole buffer pool, and others cannot really evict the context. So from this example, we see that different from traditional resource overload that multiple applications are contained for system resource. Now, even one problematic query can hurt the entire systems. And that's why we did this experiment. We run just once this problematic scan query with 100,000 like normal read-write query. And we can find that the tail latency can dramatically increase even with a very small workload. And also the throughput will bound to a low, like just 70% than the normal up like maximum throughput. So which means that in this application-defined resource overload scenario, there are several queries that cause more severe impact than other queries. But the problem is that how can we locate these problematic queries and mitigate this resource overload effect? Traditionally, this is done by using overload control. And one way is that we can run a admission control at the user side. So for each user, we kind of throttle its request frequency, or we deny some requests from the user. But the problem is that if we allow, let's say, one client to run this request, and the problematic request is in this client, it will still escape from this admission control and cause damage to the applications. And as a result, for this admission control, it cannot guarantee the SLO, the latency, or it cannot reduce the drop rate. Another way is that we try to do overload control on the queuing. So which means that we try to drop some requests in the waiting queue in order to make sure the end-to-end SLO is still guaranteed. But this way, we can only drop, when we drop this request, we choose them based on some signal, such as the SLO violation, the resource usage, and the internal application resource usage is oblivious to this queuing management systems, because this query queue is defined and used by Elasticsearch. From the operating system, it's just a heap value. We don't know exactly what's happening inside. So as a result, even these mechanisms can prevent the SLO. It will cause a high drop rate. You have to drop a lot of queries in order to make sure the system does not overload. So the reason it has this high drop rate is that it cannot differentiate this normal request from this one problematic request. So that's why in modern systems, we have designed some new techniques that is trying to trace this application resource usage from the systems and find this problematic query, and then maybe give some penalties to these queries. And this performance isolation mechanism is resource aware, so which means it knows the behavior for each request, and it can give some penalty for this problematic one. But it still cannot guarantee SLO because this is a best effort solution. Why? For example, if this noisy request hold a global log to this index, then even we know this request is bad, we cannot really schedule it. We cannot preempt the result because it holds some synchronization primitives.
The difference and the problem is that the application takes up a huge amount of the cache and evicts other things. So isn't the obvious solution to simply limit how much of the cache any particular process can take?
Yes. And so that's actually how developer fix that bug. But the problem is that so now application has hundreds of internal results. So it is inevitably that some developer will write some bugs in their code and cause this result issue. So we cannot assure that the application can always manage the results correctly.
Manage it at the system level.
From system level, actually, we cannot manage it because this is an internal data structure managed by the application.
Like the application.
Yeah, application define the resource. So it's like normally a linked list. So from system level, we cannot really handle the application's linked list.
Then I'm not clear why other applications interfere with the cache. If it's an application layer cache.
It's not other application, it's the request sent to this application.
Sending to this particular.
Yeah, particular application. And so then if one request manipulates this resource, other requests will be blocked. So then if we put all the previous state-of-art solution in the design space, we can see that the overload control system can maintain the SLO, but it will cause a high drop rate. And the performance isolation mechanisms can achieve a low drop rate, but it cannot maintain the SLO. So our goal is to design a system that can achieve both. It can guarantee the system has no SLO violation during the application-defined overload, and it only drops the particular request that manipulate the result, so 1 or 2 requests. So how do we achieve this goal? At the high level, we have adopted 3 steps. So instead of doing admission control in the request phase, we allow every request to run first. And then we monitor the application resource usage per request. And if we found some requests overload the resource and cause the resource overload and cause end-to-end performance degradation, we will drop this executing request from the applications. So by this detailed tracing, we can know exactly what request causing the issue, and we just drop this one request and without hurting others. So I will first talk about how do we monitor the performance and the resource usage inside the applications. So the challenge for monitoring application-defined results is that we have diverse types of application-defined results. They are defined by developers, and each application have their own implementation, their own usage patterns. And even the request can have different usage patterns. So for example, if we have one request, just use the query cache and the task queue, and we have a scan query coming, so the scan query will manipulate the query cache and block all the read query. But some other query, if it does not need to use the query cache, it can still execute correctly. So with these diverse dynamic patterns, we need to have some simple interface or metrics that allow us to capture this dynamic behavior. So that's why we found that despite the diverse resource type, there are 2 metrics that are common across all resources and are very important for the task cancellation job. The first one is the contention level, which basically measures how severe the current resource contention is. And the second one is the resource gain, which measures like for each task, if I drop this task, how many resources I can release and give back to the application. So think about in this case, if we have these 2 metrics, and we have a set of queries that try to access the buffer pool. And all these queries in total acquire M pages and release R pages. And it calls E page eviction for this buffer pool. And this buffer pool is an application-defined resource. The contention level just can be simply defined as the number of eviction divided by the number of page acquired. The intuition is that if we have higher eviction number, which means you have a severe contention in the buffer pool. Every time you acquire one page, you need to evict one. And the resource gain, resource usage for each query is just the page assigned to each query minus the page released by this query. So with this one, we can just uniformly define these two metrics, but there's a slight improvement for the resource usage. Because currently, if we use this resource usage, it only reflects the current usage. The request would have some future demand. It may require some resource in the later. For example, let's say this time the query one acquire 10 pages and the query two just acquire 2 pages. So it seems that the query one acquire more pages and we should actually drop this request. But actually the query two maybe just in the beginning of its execution, it may demand 100 pages during the executions. So how do we really capture this future demand is critical. If we just use the current resource usage, it would cause we to ignore this remaining resource usage, and it will favor our cancellation policy to the request that is near its finish. So that's why we refine this resource scheme to add the progress to the current resource usage. So the key idea is that now we know the current resource usage, we also know the progress, like how long this task is about to finish or not. And we multiply these two as the resource scheme. So for example, in the previous case, if the query one used 10 pages, but its progress is about 90%, then the resource gain is just 1.1. And if for the query two, if it just start 10% of its progress, so we will get 18 resource gain. So which means we will choose the query two instead of the query one. And for how
maybe you'll talk about it, but how do you know how much progress a query has made?
That's a very good question. So for us, we have defined a simple like get next model. Basically, for all the database system, we know how many row is currently executed, and we extract the how many row it will execute it, and we use these two numbers to divide it to get the exactly numbers. And so then these two variables actually is traced from the internal variables in the application. The application record the executed row and estimated row. And for other applications that does not have this clear interface, we provide an API for them to tell us the progress. Yeah. Okay. And with these two definitions, we summarize that for all application-defined resource, it can be summarized into 3 categories: the memory-related resource, the synchronization-related resource, and the queue. The memory-related resources are the resource like a query cache, internal buffer pool, or something that you will store some intermediate data. And we can use the eviction number and the resource scheme like the release and acquire to calculate it. For the synchronization, it means something that you have to use a log to protect it, synchronization primitives, like a table in a MySQL. And for queue, it's just a thread queue or a scheduling pool. And we have these metrics for different types of resource. So how do we trace this application?
The number of evictions also depends on the content of the cache at that moment, right?
Yes. So
have you figured that out?
So that's what I will talk next. How do we really treat these values? So we use a set of 3 APIs, and we need to annotate these 3 APIs in the applications to know the exactly eviction time and eviction number and the required number. And by definition, we have this get resource which basically tracks how many results you get, and the free resource is how many results you freed. And the slow by means how long you are slowed by this particular resource. So let's take an example. This is a source code in MySQL, which basically try to get a buffer page from the MySQL's internal write buffer. And it will start by just try to get a free block. If it fails, it will just try to scan and find one block to evict. And then it will go look back and get another, and search another block. And if it get it, it returns. So then we just simply, every time we found this eviction function is called, we add a slow by here, tell us that you are slowed down by this one eviction. And every time you get a free buffer page, we will add a get resource to tell the system that you get a free buffer page. And also there's another function called release buffer page. So at that time, we will call the release. So in this way, we just add these few lines of code. We can know like how many eviction times it happens and how many pages you get.
How do you disambiguate slow by and release?
Slow by is so slow by means slow down. So eviction and the release you how to say you proactively release a page.
But here you're also proactively releasing a page for a different purpose, so you can get something else in there.
So I think we also record a release inside this function. So, but not twice. So for the slow by, we only count for the every time you have an eviction happens. And for release, you can either the page is evicted, or you as a request, you can proactively release the page. Like say you finish the request and you just release all the internal buffer context. So there are two functions that will trigger a free.
No, there's no automated way to distinguish that, is there?
It's very difficult because all the application results are defined by developers. Only developer know. So actually, there is automatic way, which is a follow-up project for this one. And we just finished and submit a few uploads. It's how do we automatically find the application-defined results and find this inefficient usage.
Right now, you're looking again manually. Someone's looking at it and making a guess.
Yes, and we are doing a manual adaptation here to let our scheduler know the internal behavior. Okay, so with this, we can correctly trace the internal application results usage. Then the next question is, how do we find the problematic request and how do we safely drop it? So to find the request, the naive way is that we can just find the request that has the highest resource gain on the most contented resource. So for example, if there's a buffer for contenting, and we just release the request that use the most on this buffer. But there's a problem in this design, which is that in the application, there's not only one resource, you have a bunch of hundreds of resources. Like you have the query queue, you have the index. If we just drop the request on the most contented resource, you might be biased to just this local optimal. For example, let's say here we have two resources, the query cache and the index. And the first request have the resource gain of 100 in the query cache. The second one have 18 on the query cache and 18 on the index. How do we know which one can bring the most performance benefit to the end-to-end system? It's very hard to know because these two variables are not comparable. The resource gain between the query cache is not comparable with the resource gain in the index. They are different resources. So we, inspired by the operational research, we treat this problem as a multi-objective optimization problem, which means that we treat each resource as objective functions, that we have the resource gain, and then the goal for our system Atropos is that we want to maximize the resource gain on most resource. And how do we address this one? It can be simply treated in a design figure like this. Let's see, we just have two resources, and each request can have the resource gain for the query cache and the index. So we can see that for request 2 or request 4 is definitely best than request 1. It's dominant request 1 because in both resources, it can get most resource gains. So then we just need to find this what we call the dominant side, the Pareto front in this design space, and all the requests here are that dominant are better than other requests. Then we normalize its contention level and the resource gain to a unified unit, and we scale each objective into a single object by using the sum weight operation. So which means that the ideal is that we get the resource gain multiplied by the contention level for this particular resource, and we sum each resource. And then the goal is just to maximize this one particular function in this Pareto front. So with this, we can basically find the request, let's say request 4, that can bring the most performance benefit to the end-to-end system. Any questions for this part? Okay.
I got a quick one. It seems to me that requests 2, 4, or 5 are viable candidates.
2, 4, 5.
Yep.
Yes. Yeah, they're all.
Why is 4 the best one here?
So then for these 3, how do we choose the best one from these 3? We just get this one single objective function.
Okay.
So we just multiply the request to set this value and this value together with this is the objective function. This is a contention level for this resource.
The contention level is not in the figure, so I cannot recalculate it.
Yeah. So then we know the value for these 3, and we found the one that has the maximum like objective. And ideally, actually, either of them should be fine, but we are still want to find the best. So, and with this design, we can find the particular task that manipulate the result. So instead of just blindly drop all the requests, we just had this one like a surgery like task and just process and find this exactly task and cancel it. But this brings another problem. How can we really cancel a running request? Because previously, like in admission control, you really never run this request. The request is put in the network queue, and you can just simply drop it. But now this request is already executed in the applications. And if we just simply naively kill the thread, it will break the application's execution logic. And it might cause the inconsistent state and even some more dangerous side effects. So we need to have a way to safely cancel all the different kinds of application requests. That is here we have our observation that in modern runtimes, like the Java, the Go, or the C#, or even C++, they provide some fine-grained task cancellation mechanisms. And most applications often use these cancellation mechanisms to build their own customized cancellation handlers. Originally, this cancellation handler is used just as a functionality for users or the administrators to cancel 1 or 2 requests. But we can leverage these built-in mechanisms instead of using just naively kill the thread. And this built-in cancellation mechanism, since it's already built by application, it already designed to safely drop a request at a very fast speed. So what we do is that we provide an API for developers to tell us what is the function that will launch these initial cancellation mechanisms. And we just call it and tell them the specifically request to cancel. So here is a study we did to show the prevalence of the cancellations. We studied 151 applications across 4 languages, the C, the Java, the Go, and the Python. And we found them by the searching on the GitHub and the sort from the one with the highest star. So the one takeaway is that we found that 76% of the application already provide the built-in cancellation mechanisms. And for the application that do not provide this cancellation mechanism, they are usually non-interactive applications like a comprise some libraries that does not really need to do these resource overload control systems. And for all these applications that has the cancellation mechanisms, 95 of them provide one general interface, like one function call that will initiate the cancellations. So which basically inspire us to just give them an API to tell us exactly what this function is. Then we can launch their cancellation mechanisms. So here's just a simple example about how do we really drop the cancellations in the Elasticsearch. So in Elasticsearch, it has 1 functions, and in this function, it has these interrupts mechanisms which are used to handle the request drop. So we just tell this run request as the developer just tell us this specific function will do the request cancellations, and then we will call it to do the job.
Okay, you're relying on the developer to expose cancellation API.
Yes.
Because I mean, this could be a disaster to cancel use someone else's infrastructure, externally.
Yeah, but our tool is also a runtime library. that is used by developer. So if the developer just use our library and then use their own like cancellation mechanism. So all is done in one application scope.
They provide like fallback or something.
Yeah, fallback to our library. So it will not impact other applications. Okay. And so here is basically with this design, we have this is the workflow for the Atropos, like the resource mitigation, resource overload mitigation mechanism. So for each request, we let it run first, and we have a centralized resource management system that equipped with our automatic tracing tools, and we trace this per task resource usage and generate a big table for the for each resource. We have the contention level, the per task resource gain, and we provide this to our job request job policy engine, and this engine will make a decision from which request to job and call this callback back to the application's built-in mechanisms, cancellation mechanism, and it will do the detailed job operation. Okay. And we implement these Atropos in 3 languages, in C++, in Java, and in Go. And in C and C++, we implement it as a user-space schedule. In Java, we implement as a library class that other class can inherit from ours. And for Go, we directly integrate it into the Go runtime in order to correctly trace the application resource usage. Yeah.
How do you free the resources between canceling a task?
So the free is done by the built-in cancellation mechanisms. So
You already know the resources that that task has.
yeah, so for example, in MySQL, it defines this task cancellation as I will free all the current resource and I will just do a rollback. So then doing this in the MySQL's built-in cancellation mechanism, it already free all the internal resource. So then we just get all the resource back. Yeah. Okay. And then we will talk about the evaluation. In the evaluation, we will answer 3 questions. First, how effective can Atropos mitigate application resource usage? Second, how does Atropos compile to the state-of-art solution, meaning the overload control system and the performance calculation system? And the third, what is the overhead for the running the Atropos? So we integrate the Atropos into 6 applications, and the 3 of them are C language, and the 2 of them are Java, and 1 is in Go. And for all these applications, the manual effort is small. So we at most need to add 74 lines of code in order to annotate the internal application resource usage. But how do we exactly know the function that we need to do annotation? It takes some time. So in some anecdotal data, it takes 7 days for a PhD student to instrument these 74 lines of code. And for MySQL, which takes the most time, since MySQL has the kind of very large lines of code base, and it has a lot of hundreds of internal resource defined in MySQL. So we as a PhD student, we need to know the semantic for all the application defined resource first, and to know the function that need to do these instrumentations. For the developers of MySQL, it would be much faster, and it can be done in an iterative way. It just start to insert this annotation for some major resource, and if later they found some performance issue in some rarely used resource, they can add this instrumentation later. And for the small scale application, like say the etcd, which is a key value store, or the Apache, it just takes 2 days to finish the instrumentations because their code base are more easy to understand. And we collect 60 real world resource overload issues. And the issues are cover different types of resource, from the internal like backup log to some buffer pools to some thread queues, write-ahead log, and some query cache. And we summarize them into these 3. We summarize them into these 3 types: the queues, the synchronization resource, the queue resource, and the memory resource. So the first, we show how does Atropos mitigate the resource overload. So we normalize the throughput and the tail latency as 1. 1 means that the performance is exactly same as the normal scenarios. And when the overload happens, we can see some cases will just drop to 20% and some maybe drop to 80%. But the Atropos can always maintain the performance, end-to-end performance throughput higher than the 80% for most cases, except ones. And the reason it's higher than 80% is that by default, we set the Atropos to keep the end-to-end throughput higher than 80%. So when it's higher than 80%, it will stop to drop any request. And similarly, for the tail latency, it can guarantee the tail latency same as the non-overload case for all the cases, except one, it will slightly double the tail latencies. But in comparison, in the normal overload case, it will have much higher increase in the tail latency.
What about the cases where you have normalized throughput above 1?
Throughput, the buffer one is this one.
No, on the top figure. Normalized throughput on the y-axis, 0 to 1. And you exceed 1. So it looks like Atropos makes the system faster than it is without Atropos?
Yeah, sometimes, yes, because you drop some requests and you reduce the internal contention. Even there's no severe contention, you still have some log contention and some resource contention. And if we drop those noisy requests, you will get some performance benefit.
Okay, and then whoever submitted their request, their SOL.
Actually, no, because for us, we still have quite best to re-execute the noisy request later. If we found there's a time slot that is no resource contention, we will try to re-execute it, but it's a best effort solution. So it might still cause starvation. And one way we avoid this starvation is that we only allow one cancellation for one task. If this task is canceled once, we will not cancel it next. So it can avoid starvation. But if we cannot find a free time slot, we can drop it. It's still better than overload control, which drop 20% of the request. So then we compile the Atropos with the state-of-art solution. And we compile with particularly 4 software. The protocol, which is the state-of-art overload control system that published in NSDI 2020, which also trace the internal application resource usage, like the log usage specifically, and drop the request. The P-box is the performance isolation tool that also state-of-art published in SOSP 2023, and tries to know the internal application resource usage and penalize those ones that manipulate the internal resource. And we also have a user space scheduler, the DARC, and intro applications resource scheduler that try to schedule resource between 2 applications. And as we can see, in the throughput, Atropos can always achieve the performance goals. But for other systems, they will fail in most of the cases. They cannot really achieve the throughput higher than 80% for case 1, case 2, case 3, case 4, case 5, for most cases. And also for the tail latency, on protocol, the overload control system can achieve good tail latency. For other systems, it also fails. But for Atropos, it can achieve even better tail latency compared to protocol. The reason is because for protocol, you have to drop a lot of requests. And it's even actually overload the protocol itself to achieve a good tail latencies. And for Atropos, we only need to drop 1 or 2 requests.
Special about cases 12 and 13. For 12, Atropos doesn't do particularly well. And then for 13, everyone does really poorly but Atropos.
I see. For 13, let me check the.
These are the cases.
Yeah, these are cases. The 13 is the log synchronization cases in Elasticsearch. So it's basically you have one giant bucket query that manipulates the entire documentation. Since it's a log, so other requests actually cannot do anything. And so that's why they have really bad like tail latency. They have to wait for this long request to finish. And for 12, I think it's a CPU resource, I remember. So it's basically, this one is not really application resource. It's that we have several long idle easy requests that manipulate the CPU. And we want to test how the Atropos behave in this system resource. So it's not that good, but it's still better than than the rest.
And the 16?
16. Oh, 16 is the Go case. So for Go case, we don't run the comparison experiment because it's very hard to integrate all these tools to Go language. They are by design just used for Java or C. And also we see that compared to the overload control, the protocol, sorry, this is Atropos, not this. So our tool, the blue line can achieve like the drop rate to nearly 0%, just drop like 1 or 2 requests. But in comparison, the protocol will drop around 20% of the request in order to achieve this good tail latency. And the runtime overhead for Atropos is also very low. We run like Atropos on 5 different applications with the read-intensive workload and the write-intensive workload. And in either workload, the Atropos introduce at most 5% of the runtime overhead. And the reason is because for Atropos, we only do the very lightweight trees at runtime. And the cancellation part is the one will have high overhead. But the cancellation will only be triggered when there's a resource overload happen. So in the normal execution pace, we only suffer from this tracing overhead, which is very low in this case. So in conclusion, we found there's a new problem, which is the application-defined resource overload, that one particular request can cause more severe impact than other requests. And we want to design a system that mitigate this application-defined overload. And we design Atropos, the system that let all requests to run first, monitor the application resource usage, and precisely cancel the request that manipulates the resource. And the Atropos can achieve 96% throughput across all the cases, real-world cases, with nearly 0 drop rate. Yeah, so that's all for today's talk, and I'm happy to take any question.
What would happen when some resources are shared between tasks? Could it actually happen?
And most resources are shared, like the buffer pool is a shared resource. So what will happen is that actually most resource overload happens on those shared resources, not the single resource.
No, I mean like two tasks, like let's say they acquired something both for read. So there's no, let's say there's no contention.
Oh, I see.
And then terminating one task would not help.
For
because
this
there's
case,
already another one using the same resource.
I see. And for this case, actually, we rely on applications built-in mechanisms to protect the states. So what the application cancellation mechanism will do is that it will not immediately cancel the request that is running this shared resource. It will wait for a safe point, meaning that at this point it's safe to cancel this request without corrupt the shared data. And then it will cancel it and roll back all the things that are done by this task.
My question is that the task that you decide to cancel might not free anything, because every resource that that task is using is already used by other tasks. Could that happen?
Can you give one example? What first, for synchronization resource is not possible, right? If you hold a synchronization resource, you already hold it.
Yeah.
And for queue, is same doing resource. And for memory resource, if you hold a memory page, no one can use this page.
Then let's say one task hold 10 logs only for reads, and there are 10 other tasks that each hold every one of those logs also for reads. Killing the task with the 10 logs wouldn't help, because each of those logs are already acquired by other tasks, right?
You mean for Oh, I see. So you mean that like the 20 resource and the one request hold 10 logs for 10 of them?
No, there are only 10.
Only 10 resources.
Yes.
But if this one request already hold 10 logs and for a very long time.
No, but they're sharing the logs, right? They're only reading, so they can.
Oh, you mean read the write log?
Yeah, read only. So they can read at the same time.
For particular read and write log, it will still be useful. And actually, even for shared resource, because we are checking the contention level, which is how slow this resource calls to other applications. If even this is a shared resource, if this resource causes a slowdown and you release this shared resource from you, you can let it to share to others. So that's even it's a read logs, it may block. If it's just a read log, then you will not trace a particular slowdown on this read log because it's just read, right? You will only trace a slowdown for the write log. And then you will only release the write log, the one hold the write log instead of the read log.
So that task wouldn't be selected for cancellation.
Yeah.
Okay.
It will, but it will think the resource gain is 0. It's nearly 0, so you will not cancel. Yes.
So you mentioned that your overhead is somewhere around 5-ish% or so?
Yeah, at most 5%.
At most 5%?
Normally it's 1%
So
on average.
presumably the at most that you report is what you observed in your tests, correct?
You mean the performance data?
Yes.
Oh,
performance
we
overhead.
run the standard benchmark.
Yes, exactly.
Yeah.
So you observe at most 5% performance input from the standard benchmark.
Yeah.
The problem is I'm a security guy. So I will look for cases that are actually the worst case for your system. And I can almost guarantee you the standard benchmark never triggers the worst case.
Yeah, that's
So how do I go about to generate the worst case request patterns to make sure that Atropos is as slow as possible?
I think one way is that we kind of want to trigger a performance overload. For example, Atropos defined that if the end-to-end performance drop 20%, it will start to trigger the cancellation. And you don't give one request that manipulates the results. You give like hundreds of requests to manipulate. So as a result, Atropos will keep making a cancellation decision, and then it will definitely slow down the systems.
Okay, so the way to drive this into slow is not a bunch of small requests, but rather a smaller number of large requests. So
Yes.
requests that accumulate a lot of resources.
Yes.
Over and over treat the cancellation.
Yes.
Cool. Good to know. Just in case someone deploys that.
That'll be very visible.
I don't care.
Well, meaning I can stop
Can you?
if it's visible, sure.
Other questions? No? Well, if not,
Okay.
let's thank Yigong one more time.